University Muhammad YUSRI, project number 30066 West. I'll be starting off our presentation for assignment 3. So basically, for the executive summary, this project develops a predictive model using the byte bias dataset from Kaggle to classify whether a customer will purchase a bicycle or not. The dataset includes 1,000 records with demographic, lifestyle, and economic features. The goal is to perform binary classification based on purchase by outcome. Next is dataset description, which is the byte bias dataset. The source is from Kaggle, and the purpose is to predict if a customer will purchase a bike based on personal, demographic, and lifestyle factors. The dataset contains 1,000 customer records and include 18 features with one target variable called purchase by. This target is binary, meaning that the outcome is either yes or no. The features are a mix of demographic, socioeconomic, and lifestyle information. Some key examples include age, gender, marital status, income, education, occupation, number of cars, commute distance, and region. This variety of data helps build a well-rounded model for prediction. So next is pre-processing techniques. There is a few steps done in data pre-processing, which is the first one is data cleaning. We handle missing values by removing rows with incomplete data to ensure the consistency and reliability. And then we detected and remove outliers using ATIERA method. We visualize the data using box plots before and after outlier removal. So we can see here there is for income there is 8 outliers detected. So this is the box plot before outlier removals, and this is after outlier removal. Same goes to others, which is children, and there is 0 outliers detected. And for cars, there is a few outliers detected here, 51 outliers detected, and age there is 4 outliers detected. For the second step is data transformation, which is skewness correction using log transformation for skewed numerical columns. So for highly skewed variables, we apply a log transformation using the log1p function to reduce skewness and improve the data distribution. So here is skewness visualization of skewness correction. We can see here there is before and after skewness correction. After that, we normalize numerical data using min-max scaling, which is range 0 to 1, so that each feature scales between 0 and 1. For the next step, which is the third step, is categorical encoding. Basically, we convert categorical columns like gender, marital status, education into numeric format using one-hot encoding. This process converts the categories into numerical variables suitable for machine learning algorithms. And then for the first one, we perform feature selection using the random forest feature importance method. Basically, we identify the most important features or variables that influence whether a customer purchase a bike. So we can see here the most important features or variables that influence whether a customer purchase a bike is age.
For this part of the project, our goal was to predict whether a customer will buy a bicycle based on their demographic and lifestyle attributes. We chose the random forest classifier as our model because it performs very well in classification tasks, especially when handling dataset with both numerical and categorical features. It is also resistant to overfitting, which helps ensure our predictions generalize well to unseen data. To prepare our dataset, we encoded categorical variables such as gender, marital status, and region using label encoder. And we normalized numerical features like age and income using standard scaler. This step ensured that the model could process the input data consistently. Next, we performed train test splitting using 9 different ratios from 90 to 10 all the way down to 10 to 90. It is to make sure our evaluation was fair and unbiased. We used stratified sampling, which helped preserve the balance between bias and non-bias in each split. Each model was trained with 100 decision trees, and we repeated this process for every split to see how the amount of training data impacts performance. To evaluate the performance of our model, we use 5 key classification metrics. First one is accuracy, precision, recall, F1 score, and ROC AUC. These metrics gave us a well-rounded view of the model's effectiveness. Accuracy told us how many predictions were correct overall. Precision and recall helped us to understand how well the model handled the positive class, in this case, identifying actual bias. The F1 score combined both precision and recall into one balanced measure, and ROC AUC showed how well the model distinguished between the two classes. Among all the trained test splits, the 90 to 10 ratio performed the best, achieving the highest F1 score and ROC AUC. This indicates that with more training data, the model learned better patterns and made more accurate predictions. In conclusion, this modeling process shows how the importance of proper pre-processing, balanced sampling, and comprehensive evaluation. It also confirmed that random forest is a strong and reliable choice for binary classification problems like this.
So the next part was the performance evaluation. For this section, it explains how we measure the accuracy and the effectiveness of our model by trying out different trend test split ratios and comparing their result using standard classification metrics. The evaluation was done by testing the model using 9 different trend test split ratio range from 10 to 90 to 90 to 10. The purpose of this evaluation was to analyze how much training data affects the model performance and to find the best ratio for prediction accuracy and generalization. So we use 5 key classification metric, that was accuracy, precision, recall, F1 score, and ROCAC. Which was stated before. The accuracy tells us the overall percentage of the correct prediction from the model, and precision tell us how many the customers of the model predicted would buy a bike that were actually correct, and recall checks how many the actual bike buyers that were successfully identified by the models. And then we have F1 score. F1 score combines precision and recall into a single value. It was useful to see whether the dataset might be imbalanced or not. And lastly, we use ROC AUC. This tell us about how well the model distinguishes between the two classes that were biased and non-biased for this project. So next we move to the first model that we developed, that is result table for all splits. Here the table summarizing the performance results for each test split. Each row show how the model perform under the specific configuration, and we notice that the model performance improve as we increase the training data. For instance, in the 90 to 90 split, the model struggled due to limited training examples. But as we move towards the 70 to 30 and 80 to 20 splits, the metrics like accuracy and F1 score steadily increase. And this indicates that the model learns better and makes more confident prediction when trained with more examples. And the next one, we move to the line chart for the metric trends. So when we look at the line chart, this line chart help us visualize how each metric changes as the training size increase. So We can clearly see the upward trends for accuracy and ROC AUC, confirming that the model become more effective with more training data. So the larger the training data, so we can see the increasing in the trends for accuracy and ROC AUC. For the F1 score, uh, it is also increased and reached its peak at 90 to 10 split. Uh, this graph also tells us that the training data plays a key role in boosting model performance, but after around the 80 to 20 split, the improvement begin to level off. It went static. The next one was F1 score bar chart that we generate. So from this bar chart, we focus on the F1 score that consider both precision and recall. So we can see from the picture that the 90 to 10 split stands out with the highest F1 score that is 0.75. This indicates that our model didn't just make an accurate prediction, but also it balanced the correct identification of both bias and non-bias. So this kind of balanced performance very important in real business application like to target customer for promotion. And the next one, we move to the conversion matrix of 90 to 10 split. So we use conversion matrix to summarize our model's prediction result. So from this conversion matrix, we can see that out of 100 customer, the model correctly predicted 45 non-bias and 33 actual bias. Um, from the conversion matrix, it made 10. We can know that it made 10 false positive error, where the model predicts some customer would buy, but the customer didn't buy it, and it also make 12 false negative, that it was the missing actual buyer. So from this conversion matrix, we also can calculate the overall accuracy. That is, we can after we calculated it was 78%. The precision was 76.7, where it where it has the meaning that most predicted bias were actually correct, and the recall was 73.3. So we can know that the model detected it was this model detect most actual bias. So for the last part of the performance evaluation, uh, we move to the ROC curve for 90 to 10 split. So when we look at the curve, it can show how well the model spread the positive from negative class at various thresholds. So for this curve, the closer the curve to the top left corner, the better. So when we look at the curve, our model achieved an AUC of 0.8578, which is considered excellent. Uh, and this confirm that our model has a strong ability to distinguish between bias and non-bias, regardless of the classification thresholds. So, in the conclusion of performance evaluation, our performance evaluation proved that the random forest classifier was suitable and effective for this binary classification task. The 90 to 10 split that we provide was the best performance for overall, and it also offering a good balance between the precision and recall. We recommend using this configuration for future projects with a similar dataset. That's all for performance evaluation.
We evaluated the random forest classifier across multiple train test split ratios ranging from 90-10 to 10-90. Each configuration was tested for its performance in terms of accuracy, precision, recall, F1 score, and ROC AUC. Out of all the configuration, the 90-10 split stood out the best performing one. This means that 90% of the data was used for training and 10% for testing. Why was this the best? Because it gave us the highest accuracy at 78%, the highest F1 score of 0.75, and the highest ROC AUC score of 0.8578. This combination shows that the model could not only correctly classify the data, but also generalize well to new unseen data. Although the 80-20 split had slightly better precision, the 90-10 split gave us the best balance between precision and recall. This balance is very important in classification tasks, especially when both false positive and false negative methods. Also, with 90% of the data used for training, the model had more data to learn from, helping it capture more patterns and improve overall performance. So, based on of this metric, we selected the random forest model with a 90-10 train test split as the most suitable and reliable configuration.
In conclusion, our project was about building a model to predict who is likely to buy a bike using the bike buyers dataset. The dataset has 1,000 records with information like age, income, job, and lifestyle. We choose to use the random forest classifier because it works well with different type of data and give good result without needing a lot of changes. Before training the model, we clean the data. We remove missing value and outliers, fix uneven data using a log transformations, scale the numbers to the same range, and change text data into numbers using encoding. This made the data ready for training. Next, we also use a random forest to find which features are most important. We found that age, income, number of children, and number of cars are the top features that affect whether someone will buy a bike. To check how well the model works, we use 5 performance measurements, which is accuracy, precision, recall, F1 score, and ROC AUC. This helped us see if the model was good at correctly predicting both buyers and non-buyers. We test different train tests split and found that the 90-10 split worked best. It gave the highest accuracy of 78%, an F1 score of 0.75 and a ROC AUC of 0.8578. This means the model learned well from the training data and could still give good prediction on new data. So overall, our model worked well and could be useful in real situations like helping businesses target the right customer in their marketing. Last but not least, based on what we found, here are some recommendations for features, project, and real use. First, we suggest using the 90-10 split again in similar tasks. It gives the best result in our testing. Second is a random forest should still be used for this kind of data. It handles mixed data type well and gives strong result. We also recommend using a bigger data set in the features, more than 1,000 records. This can help the model learn better and make more accurate prediction. Next, it's a good idea to try other models like XGBoost, SVM, or neural network. They might give even better result and help improve the project. We also suggest using the model in a real business system like a dashboard or CRM. That's why businesses can use the predictions to focus their marketing on the right customer. Lastly, when working with unbalanced data, it's better to focus on F1 score and ROC AUC. not just accuracy. This give a clear picture of how well the model really performs. So, by following this step, future project can build better models and help company make smarter data-based decision. So, that's all from us. Thank you.